So for the last couple of weeks, we've been talking about a finite state automaton or regular expression model of computing. And basically, these models of computing are meant to represent what a computer could do if it had a very limited amount of memory. So essentially, these computers are able to keep track of just a few things. So maybe you could think of a CPU along with access to registers might be the idea here, or just a very, very small amount of working memory. Or would be a good example of something that would be similar to a finite state automaton model of computing. And kind of like what we saw with the circuit-based model of computing, in practice we can see this finite state automaton model as being advantageous because of its ability to avoid memory accesses. So the thing that really makes a lot of computing really slow is actually the amount of time spent in that von Neumann bottleneck. So waiting on things to load in from memory. So being able to limit the amount of memory when it is typically going to be overall a good thing for computation. Not always, but very often. So because of this finite state automaton and regular expression model of computing is actually going to be useful in a lot of applications. There's also this added advantage when you're looking at this model of computing that it is sort of a streaming-like model. So when we looked at the execution model for our finite state automata, the fact that it was this like read once, no going back input model meant that you could sort of just stream in your input as you went along, and you don't have to sort of keep track of it, or you don't have to sort of wait for all of your input to come in before you can start working on it. You can start working on your string if it's being downloaded over the internet or something like that, even if you don't have all of it yet. So some use cases where these regular expressions and finite state automata are going to be useful include things like bioinformatics. So you saw this with one of your homework problems, that you were looking for certain genetic disorders using these finite state automata. Sort of a more generalizable way that this is applied is in something called read alignment. Typically, when you are doing sort of genome sequencing, instead of sequencing the entire genome at once, what you'll actually do is you'll take somebody's DNA and you'll chop it up into a bunch of little pieces, and then you'll sequence those tiny pieces first, which are called reads, and then you assemble those reads together in order to construct the entire genome. So you try to piece back together like a puzzle how those individual snippets of genes ought to go together. And the way that you do this is you actually have some sort of master genome that's available to you. So the Human Genome Project was basically intending to build this master genome that will allow you to sort of get good ideas for where the individual reads might fit in best, because DNA from person to person does not change all that much, so this can sort of help you to get a good idea for where the pieces might belong. Doing this matching of where should an individual snippet of DNA fit in the entire genome can be done a lot of times with finite state automata like models of computing. Also, you can do a lot of virus scanning if you're downloading some sort of program or you're downloading some sort of information onto your machine. Then a lot of viruses have these signatures that you can represent with regular expressions. So you can do a lot of antivirus software, with some of this with regular expressions. There's also been an application in higher energy physics that uses finite state automata. That basically, when in a particle collider, you just smash some subatomic particles together, and they send their little itty bitty pieces all over the place. what they're doing is they need to sort of track the path of all of these little tiny super subatomic particles, and that can actually be done with finite state automata. So there's some of these surprising applications that you might have with regular expressions in finite state automata that maybe you didn't predict might be there. So if any of these interest you, if you liked finite state automata, if you liked any of these applications, feel free to come talk to me. I'd be happy to discuss more in depth what's going on with some of these. As we move on to this week, though, what we're going to be talking about is sort of the bigger model of computing, which is Turing Machine. So this is the model of computing that's going to be kind of like a finite state automaton, but we're going to have access to memory. So memory has been the thing that makes our previous models of computation somewhat weak in the way that and how much memory they have access to and the ways that they're allowed to use it. But it's also what makes a lot of these applications really interesting. The Turing machine model is meant to be the grandest computing model that we have. It's meant to represent everything that we could ever hope any computer could do, including us as humans. So we're going to be talking about what is a Turing machine, why is the memory important, why do we think that it is so powerful, that it is sort of the last word in computing models, and why we think that it is roughly equivalent to humans.